just to let you know that we do now have presenters and presentations lined up until the middle of September, and we have got all sorts of different topics lined up. A lot of them now are sort of not so technical, so we've got presentations on heat pumps in the rural environment and farming. We have got information. We've got David Boone from the British Geological Society comes to talk to us about the tools that they have. We've also got information on funding of heat pump projects. So we have got quite a few different talks lined up, as well as still some technical talks as well. Next week, we have got Ken Neal from Solid Energy talking to us about the importance of flow temperatures and heat pumps and operating them for high efficiency. So there'll be some nuggets of information in there next week. So if you are free, come along. And of course, as usual, these are recorded, so you can catch up on YouTube afterwards. So it's now nearly 1:05. I am going to hand over to Chris, but just to remind you, please do use the chat function for any questions that come up. So over to you, Chris.
Thank you very much, Laura. Super introduction as ever, and thanks for fielding the questions for us. So as Laura said, we're going to be talking about heating and cooling, with the emphasis on cooling. So most of us are familiar with heating using ground source systems. I'm going to talk about how easily and how effectively those systems can then be used to do some cooling as well. So why include cooling? First of all, improved efficiency. If we can put something back into the ground, then we are going to be warming up that ground loop, particularly when we've got simultaneous heating and cooling going on. But also we can actually store energy over a much longer period of time than perhaps people realise. So we get improved efficiency. We can also get lower installed costs, and I'm going to do a couple of case studies in a few minutes to illustrate how those costs can be dramatically affected by the inclusion of some cooling in the project. More bang for your buck. Put quite simply, the same box can do heating as can do cooling. So you don't have separate boiler plant and chiller plant. So it can be a very effective and indeed reduce your plant space overall versus conventional. We can get rid of external equipment entirely. So it's quite a useful opportunity to get away from any architectural concerns about external cooling equipment, structural concerns with having cooling equipment on the roof. And I even designed some mobile phone mast cooling systems in North Africa. And the reason they wanted all the equipment internal to those systems was because people nicked the external equipment. So there can be lots of reasons why you'd want to get rid of that external equipment on a system. And finally, I alluded to it earlier on, we can actually get significant quantities of interseasonal energy storage with these systems. And if you think about it, that's a real holy grail as far as heating and cooling systems in buildings is concerned, to actually recapture some of that energy that's dissipated into the ground in the summer and bring it back in the winter is really a massive step forward for heating and cooling. Now, what I'm going to be talking about today is primarily around boreholes systems, but the same does apply to horizontal systems, but not exactly the same. The physics of horizontal arrays, because they are much closer to the surface, is slightly different to borehole arrays. So for example, when we're designing a horizontal system, we need to put some weather data in there, where the weather data for a borehole system is practically nothing more than the temperature of the ground as an average throughout the year. So there is some physics differences between horizontal systems. Put succinctly, a horizontal system will not store heat as effectively as a borehole system does. So those are the reasons why we like to include cooling in any ground source system. So this is how active cooling works. So on the blue ground loop there is a heating ground loop, where we're putting cold water into the ground. That water is sucking heat out of the ground. The heat is then put into the heat pump. The electrical energy consumed by the heat pump also ends up as heat, and we then put that into the building. Technically, this is called heat of extraction, so the heat we're extracting from the ground, and heat of rejection, the heat we're rejecting into the building. We can simply reverse that process. So if we start to now put hot water into the ground. So we're sucking heat now from the building. The compressor energy ends up as waste heat within the heat pump again. We're then rejecting that heat into the ground. So we're putting water into the ground, maybe 25, 30 degrees C, to push that heat back out into the ground. But it's a symmetrical process, except for the fact that in heating mode, the electrical energy consumed by the compressor helps you to heat, and in cooling mode, it actually hinders you. So you're actually rejecting extra heat because you're getting rid of that compressor energy into the ground as well. It's an important point to realise that you'll very often see very complicated spreadsheets with consultant engineers trying to balance to the nearest kilowatt hour the energy taken from the building or put into the building, but that completely forgets the point that the compressor energy is added to in heating mode and contributes to the load on the ground in cooling mode. So that's how active cooling works. It can be done in one box, as I've shown here, with a reversible heat pump. And effectively what that does is it swaps the heat exchangers round on the compressor. So that's a reversible system. Or it can be done more simply by having two heat pumps, one dedicated to cooling, one dedicated to heating, and sharing a communal ground array. So that can be, it's all about horses for courses, and there are differences, disadvantages and advantages to both approaches, but they're entirely valid. Obviously, as we build bigger systems, then we may have more heat pumps connected to the ground array. If we now contrast that with a passive cooling system, we've got a heat pump here that's dedicated to heating. This is not a reversible heat pump now. This is just dedicated to heating. And all it does is it sucks heat out of that ground loop and put it into the building. But because that ground loop is now getting colder, we can run it through a heat exchanger, as is shown here, and we can use that heat exchanger to suck heat directly from the building. Now, the advantage of this is that we don't have the compressor energy in the cooling side of things. We're simply running some pumps. So it can be a significantly more efficient way of cooling, provided the temperature regime in this ground loop is correct for passive cooling. And what that generally means is it's significantly heating dominated building. So that ground loop's going to get cold and it's going to stay cold throughout its life. But as I say, a very effective way of cooling with very low energy input. So I'm going to give you a couple of examples now. So this is a fictitious school in the Midlands. I've just picked it because I used to use my own postcode and I'm based in Leicestershire. It's 100 kilowatt peak heating load, and that's the annual kilowatt hours delivered in heating. What I've done there is I've used local weather data to come up with what is a sensible load profile for this type of building. And let's imagine we've got a 20 kilowatt peak cooling load. So maybe it's just our ICT suite or the staff room, something like that. So relatively modest loads for cooling. And again, I've used local weather data to come up with this annual requirement. I've used a thermal conductivity of 2.1, middle of the road, low to middle of the road for the UK, and an undisturbed ground temperature of 9.8. And as I said earlier, I'm going to concentrate on vertical boreholes. So if we look, first of all, at emitting the cooling entirely from the system, then we're looking at 2,508 meters of borehole in whatever configuration. We discussed that a few weeks ago, how important designing to a specific configuration is and sticking to that. So if you haven't seen that webinar, it's worth going back and having a look at it. If we now add that cooling demand in, then we reduce the requirement using the same temperature profile in the ground. We reduce that requirement to 2,256 meters, which is obviously a significant saving. To put that in monetary terms, we're saving about £14,000 on this project, which would equate to about 7% of the project install cost for the system is being saved by including that cooling. In addition to that 7% savings, which is just purely on the drilling, we would also be saving because we wouldn't be putting conventional cooling equipment on the building. So there would be additional cost savings involved in it as well. On this model, we've run the loop temperature, so I'm going to show you some graphs in a second, and the maximum loop temperature gets up to about 12 degrees C. So in this instance, we do have the opportunity to do some passive cooling, provided we can design around a temperature of about 12 degrees C in those cooling circuits. If we look at the two graphs here, now apologies, the scales look a little bit odd on this, but the ground loop design software we use doesn't allow me to rescale. So what I've done is I've squidged this one down so that we've got 0 degrees here at the bottom, 5 degrees here, 10 degrees here, and that's the same across the two. So if we look at the heating only ground loop temperature profile, then we can see that it marches down. It tends to a limit at about year 20, where it stops getting any colder, but that ground is depressed in temperature throughout the life of the system. If we now look at, and it gets up to a maximum of the undisturbed ground temperature, which is 9.8 degrees. If we look at the heating and cooling system now, you can see that during significant portions of the year, the ground loop temperature is well above that undisturbed ground temperature. So what that means is that we are getting, particularly during those warmer seasons, we are getting very, very effective heating for domestic hot water and anything else that's required for heating during the warmer period. And we're also recovering heat between the seasons as well. If I look now at a second example, so same school in the Midlands, but we've got a much higher peak cooling load now and a correspondingly higher annual requirement for cooling. Everything else is the same. And if we run it, obviously, and emit the cooling, we get the same number as before, 2,508 metres of total borehole requirement to do that load. If we now look at adding the cooling into the system, then we take that down to 1,536 metres of borehole, which is obviously a dramatic saving. Now, the run cost, the approximate install cost savings for the boreholes alone on this is about £39,000, so a very significant saving on the project. About 10% of the project costs for a system of this size. And indeed, again, we are not including any delete costs for conventional equipment in this, so a very significant saving overall. In this instance, however, the maximum loop temperature goes up to about 25 degrees. So passive cooling isn't really an option for us in this instance. So we've got to look at not just the loads on a peak and an annual basis, but we've got to actually model those ground loop temperatures. And again, if I show you the graphs, that's the same graph as before, just the heating only. And you can now see that our summer temperatures are getting up very significantly. So just in summary, before I take some questions, grab cooling whenever you can. Most of the systems I've designed over the years have been heating and cooling systems. The economics tend to be much better when you've got a cooling load involved in the system, as we've illustrated above. Any other heat recovery also works. So, for example, we were just talking earlier on, Laura and I, you could put some solar thermal onto a ground loop just to reject some heat into that ground loop and get the similar benefits. You can connect different buildings together and take advantage of the different load profiles. You might have a school and a data center. They would be a natural mix, or a hospital and a data center. Those kinds of things. Just try and think about any type of heat recovery you've got and use the ground loop to do that heat recovery because of its interseasonal abilities to store. Do not try and design one of these without proper software. The MCS tables are not equipped to design any cooling systems on any systems of any size. So please use a professional to run a proper piece of software through to design them. And then finally, explore your passive and active options. Are there opportunities to maybe manage that heat, that cooling load down a little bit and go to a passive option? Or actually, do we have to go to an active cooling mode? So with that, I'd like to open up to some questions, Laura. I can't unmute you, Laura. Is Charlotte about? Oh. Please bear with us.
Yeah, right. Hello.
Oh, wait.
I'm back. Hello.
Excellent.
Thank you, Chris. That was really, really good. At the moment, I don't think there is any questions in the chat box. So okay. Can I just encourage people to have a think and put some questions down there? In the meantime, I just have a question, which is, you talked about, you showed two pictures, one heat pump doing heating, one doing cooling. What about if you have a heat pump that does a simultaneous? What does that then look like? You've got the left side heat pump, you've got the right side, but sometimes we might want to run a heat pump that's doing both at the same time. How does that balance in the ground?
Okay, so in most instances, when you've got a simultaneous heat pump, it'll have a pair of hot connections and a pair of cold connections for your heating and cooling circuits respectively. And then either the ground loop will be connected to either the hot circuit if we've got too much heat, or the cold circuit if we haven't got enough heat in the system. So that's one way of doing it, or it can all be done inside the box, inside the refrigeration circuit. As far as modelling it's concerned, it's very similar to whether it was separate heat pumps or if it's simultaneous heat pumps. The benefit of doing it with a simultaneous heat pump is that the same compressor energy that drives your heating is also driving your cooling at the same time. So whilst I haven't included it in these schematics, it is a more efficient way of doing things. But just be aware, you could put yourself in a bit of harm's way with things like RHI. Yeah. Which it does make things more challenging. You're the expert, Laura, but it does make things more challenging when you're looking at simultaneous heating and cooling in a system.
And metering that, yes. Okay, that's brilliant, thank you. I do have a couple of questions now. So Nigel Bobbs from Retherms on the chat. What might be the difference in effectiveness? So you said that boreholes are more effective than horizontal, but can you quantify what the difference might be between effectiveness of a borehole system to a horizontal loop system in terms of heat and cool?
It depends on the ground conditions, Nigel. That's the most important thing to point out. But as a rule of thumb, you get practically no interseasonal energy storage with a horizontal system. It's very, very minimal. Whereas in a borehole system, you could be able to recover up to 90% of that heat that you've discharged into the ground in the summer back in the winter. But generally, your horizontal systems, because they're so close to the surface, will just propagate that heat up and out to the atmosphere. So it's a minimal effect with horizontal, whereas in vertical boreholes, it can be very significant.
Okay, and just a follow-up question to that. Is there actually a minimum size of system to be effective? So if you might be looking at, say, I'm guessing sort of a more small domestic size or small commercial, maybe 10, 20 kilowatts, is it still effective, or do you need to be up in the hundreds to thousands of kilowatts?
No, I mean, if you're looking at a small reversible heat pump, it can be effective. I've done systems down even at 3 kilowatts for district type apartment buildings and so on, where cooling is increasingly becoming a problem. So no, it can be effective really at any size. I would just caveat that by saying that the distribution system for heating and cooling is obviously a significantly different animal to a heating only distribution system. So you'd need to consider that as part of the equation. But from a heat pump and a ground loop point of view, you're always going to be winning if you get some cooling in there.
Okay, thank you. And I think it is really important that the message you gave towards the end, which is if you're looking at heating and cooling systems like this, you absolutely have to get an expert on board. I think otherwise, the idea is great, but if you don't get the design right, it can go horribly wrong, which I'm sure you are very well aware of, Chris. And then we've got a question from Rich Davis. This is a good question. What percentage of systems are installed with cooling? Is it a missed opportunity? And what questions should be asked when engaging the client to expose the opportunity? So any thoughts on that?
Well, I think it's a depressingly low amount of systems go in without cooling, because many people just don't recognise and understand that cooling can be done with ground source. Many installers aren't comfortable doing heating and cooling systems. They've just always done heating only systems. And so I think there's a lot of education needed out there in the marketplace to let people know, and this is why we're doing this today, let people know that heating and cooling can be done. And I think as far as prompting customers to think about cooling, it's just part of what we do as a designer when we're doing feasibility studies or designs, we're constantly asking, do you have any cooling loads? Do you have any cooling loads? Just because we're used to doing that. And I think many people in the industry don't, which is a shame really, because it's heat being lost to a split system or something like that that's going into the atmosphere and will never be seen again.
Yeah, yeah, and I think that the more people like that go out to site, start saying to clients, do you need cooling? Maybe that will start to sow the seed with other clients who then think, yeah, first question, do we have any cooling? That's where we want to be, isn't it? So,
get some nice case studies out there. You know,
yeah.
we are very bad in our industry at doing case studies with good data in them. So it's worthwhile looking at that.
Yeah, okay, thank you. Hope that answers the question, Rich. So John Findley's got one here. This one I'm interested in as well, actually. Do you know of any active system using solar panels or PVT to charge the ground loop? So anything that's happening now?
We've done a few social housing with solar PVT attached to ground loops. So we're cooling the solar thermal element of the PVT panel, which has the benefit of reducing the temperature of the PV panel, which in turn enhances their efficiency. And then we put that heat into the ground. So a very simple system. We've done a few pilot projects. Kenza are doing, we've done some with them for some social housing providers out towards Gloucester. So there are some systems installed, and it's like many things, getting back to the case studies, John, it's often the case that there are plenty of them installed, but just nobody chooses to talk about it.
Okay, brilliant. Hopefully we'll see more, and then we'll have more out there in the field to go and look at. So,
yeah.
Okay. So Dave Bedford has a question here. What is a realistic capacity of interseasonal thermal storage? Will you be able to store everything you recover, or a percentage of that? Follow-up question: will groundwater conditions affect this, the interseasonal thermal storage aspect?
Absolutely. If I can take the second bit first, groundwater conditions make a huge difference to how much energy storage you can do and how effective it is. I've run models where it can be as effective as 90% of the heat you discharge into the ground hangs around. If you're in a nice, heavy, dry clay, as you are in London, for example, if you stick within the London clay, you're in a very heavy, dry clay there. And it is incredibly effective at storing energy interseasonally. But if you go down into the chalk beneath the clay, you will almost always have moving groundwater, and that will just wash any heat away for you. So it could be as low as almost zero, and it could be as high as at 90%, depending on the geological conditions, whether it's an aquifer, whether it's dry ground, and so on. One interesting thing that I've done a lot in central London is use loops within the London clay as our interseasonal energy store, and then boreholes into the chalk to then balance that. And that can be an effective way of working with the ground. As we're talking about in previous discussions, you've got to work with the ground conditions you've got. You can't fight them. There's no point. You will lose. And so you just have to work with what you've got, and spotting opportunities like that to maximize your energy storage using one layer and then potentially using other layers to do other things can be very interesting.
Okay. So did you answer the first bit, which was, will you store everything you recover, or will it be a percentage of that?
It will be a percentage, anywhere between virtually nothing and up to, I've seen it up to 90% of energy recovery. Brilliant.
And I think, again, that reinforces the message: you need an expert on the job.
Yeah.
You know, you'll think understanding ground conditions, that's very specialist. But there are people like you, Chris, and others who are in the GSHPA who understand this, and you absolutely need to be engaging with people like yourself to work this out properly.
Yeah, I think it is important. And, you know, if you're designing a system to rely on energy storage and you've just got no hope of getting it because you've got groundwater heaving through the system, then the good news is you've got very good conductivity, so you'll probably be okay. But I don't like designing around the word probably.
Yeah. Okay. Good question from Nigel. Another question from Nigel: can you add cooling as a retrofit?
Yes, Absolutely. Again, you need to check the design is capable of it, but generally speaking, as a rule of thumb, if you've got, say, 60% of your heating load as a cooling load, you could just pop that straight in, and your heating efficiency is going to get better, and you'll be cooling very effectively as well. So yes, absolutely can be done. And similarly, you know, you can add, once you've added your cooling in, you could probably add more heating capacity in there as well. Again, you need to run a model to check it, but yeah, it certainly can be done.
Great, thank you. And we have a question from Peter McConvey. He has said, is there any influence on decisions on borehole spacing, whether you're doing heating only or heating and cooling, or does that just form part of the standard modelling design? So
that's a really astute question. Thank you, Peter. Very good. Yes, heating only systems, you tend to need to spread the boreholes out more to keep your borehole quantity down, your overall meterage down. So where we're doing heating only systems, we could be up at 10, 12, 14, even 16 meter spacings to minimize that drilling if we've got space available. When you get into a more balanced heating and cooling system, you can start to compress those spacings down. And actually, you don't just not lose, sorry, you can actually win a bit, because you're actually packing your boreholes together and you're creating a more effective thermal store. And it's something that we can do in our design software, and the other design softwares that are out there can do it, is you can start messing around with those spacings to see where the optimum is. And you can see if it's starting to be heating driven or cooling and heating is starting to balance in the system. And with experience, it's a really interesting thing to mess around with, actually. But then I'm quite sad.
No comment. Well, okay. Actually, I thought we were just at the end of the questions, but another couple have popped up here. Another one from John Finlay. Do you have a view on the claimed significant benefit of the coaxial closed loop borehole installations being brought in from the USA?
Yeah, it's interesting. I'll not talk specifically about the coaxial one, but all what I would call miracle loops. So I'll just talk about them all. There are some very clever designs that people have worked on that can give you very, very high thermal transfers around a borehole, be it a coaxial, be it multi-probe heat exchangers, innovative materials, everything else. But fundamentally, they will not give you what the ground will not give it. So if you are not designing them for the ground conditions, you might think you get a very high thermal transfer, and you will be getting that around the coaxial heat exchanger itself. But actually, if the ground won't give it to you, you can't take it out. So you've got to be very careful with a lot of the claims you see. Yes, if you put a coaxial heat exchanger in rock salt, you're going to get huge conductivity out of that. Or if you put a coaxial heat exchanger in a condition where you've got saturated sandstone, for example, again, you've got huge conductivity from that. But that is not a universal ground condition. And you've got to know what you're doing. So there are, unfortunately, quite a lot of claims out there in the marketplace that, whilst they are substantiatable, if that's a word, in a laboratory environment, you've got to design it for the ground conditions you're working to.
Okay. Is that okay, John? Hopefully that's answered the question. There has been another question actually just about the RHI and how cooling affects the RHI. I don't know whether you want to say anything about that, Chris, or do you want me to
yeah, I mean, I'd like you to answer that, Laura, if you don't mind.
So yeah, I mean, it's a question from Nigel, and it's definitely not a daft question at all. There aren't, well, in my opinion, there are no daft questions in this. So simultaneous heating and cooling heat pumps are definitely eligible for RHI. Air source not, but we're not talking about air source today anyway. But ground source, yes, but the metering has to be absolutely spot on, because you must be able to show use of the heat pump for cooling and use of the heat pump for heating, and you must have your metering spot on for that. Otherwise, you are you are going to fall foul of Ofgem, and they are very, very tight on that. So hopefully that's the answer to that. So yes, you can do it, but be very careful about your metering. Martin Fowler, why do many installers perceive that cooling only works with boreholes and that ground strings don't really work if cooling is required?
Yeah, it's an odd one, that, Martin. Yeah, all of the options we've got with ground source work for heating and cooling. Perhaps it's a misunderstanding of the comment I made earlier on about the physics of horizontal being different from the physics of boreholes in that they don't store as much energy, but they work perfectly well for heating and cooling, provided they're designed properly. So yeah, absolutely. It's one of the many misconceptions that's out there in the marketplace.
Okay. Do we have any other questions from anybody? I think we have got through them all at the moment. So if anybody does have questions after this, or of course, you know, if you know anyone who wants to watch it on YouTube channel, then the contact details are there on the slide that you can see. So contact the GSHPA, contact Chris. I know he's on LinkedIn, and you're quite easy to find on the internet, Chris. So yeah, just get in touch with him directly or through the GSHPA. So if there's no other